Welcome everyone to today's version of the Inverse Problems seminar. So I'm very happy today to have Mourad Sini from RICAM, an expert on analysis on complex media and inverse problems, material science and related issues, challenges. And we're happy that he will be talking about high transmission acoustic resonances for quantitative ultrasound imaging. So thanks so much for coming, Mourad.
Thank you very much. So first of all, I would say good morning for all of you there and good evening for others, maybe in between for others also. Okay, then if first of all, I would say that this is a joint work with several of my collaborators that I cite here. The first of them is Andrich, the other one is Langley, and also Suman Sinapati. So I thank them for this collaborations. As you see in the talk, in this title, so you can see two parts. The first part is high transmission acoustic resonances. So we'll talk about resonances. And then in the second part is about quantitative ultrasound imaging, and we see or inverse problem in those imaging modalities. And the target is to give you some understanding that we reached in using such resonances in imaging. Okay, so then why resonance? Why this comes from? So in the recent years, we were interested in imaging modalities using contrast agents. So the medium is perturbed in different ways by a small contrast agents. And here I show you two pictures. Actually, you can find many works in the literature. The one in the left here are using as contrast agents nanoparticles, okay? And one in the left and one in the right are using microbubbles. So what I say here is that after, if you compare the image before and after embedding the contrast agent, then you really see a contrast in their image. So this means that imaging with contrast is useful, especially if the image itself is not highly contrasted. When it is highly contrasted, then obviously this might not be needed. But as soon as you are interested in imaging with low contrast, then creating it may make sense. And in many of these works, they also talk about the resonant effects created by this contrast agent. They do not name them quantitatively, but they say that the fact that they are resonating help to have such kind of contrast. So this is the background where I was interested in. And then I would like to propose some understanding of this. Obviously, we start by stating really conditions where we can do a proper or clean analysis. Then I would start by saying that few scenarios and assumptions where we can do the analysis are the following. In the first part, we say that the contrast agents are injected in isolation. Okay? Isolation means putting them one after another, and they are well separated. Of course, this is a mathematical assumption. In practice, this might not be exactly what is done, but let's say these are the conditions where we can do some analysis. And why is this? Why this makes sense to us? Because in this case, we can avoid strong multiple scattering. We can put ourselves under weak multiple scattering. So the first part is when we put this contrast agent injected one after another and well isolated. In the second part, being closer to reality than in the case where we put them all at once, in this case, then strong multiple scattering cannot be avoided. And here we define two scenarios where we can do something. The first one is these contrast agents are distributed in a certain regular form, for example, periodic or following certain given and smooth density of distributions. And then in this case, we can think of deterministic estimates in terms of inverse problem. The next step, which we find very interesting, is when we inject those, when we introduce certain randomness in the distribution of this contrast agent, in that case, we would need probabilistic estimates. So in this talk today, I will give you most of the parts here and probably also here, and indeed this part here. Okay, so I put here green because we have a clean understanding. I put it here yellow because we have some ideas how to do it, but this one wasn't done yet. Okay. Good. And the main principle, I just write it here. So this kind of contrast agent, they have high contrast. For example, for bubbles, which is the main contrast agent we use in acoustics. These bubbles, they have high contrast. I will show you later what do I mean by high contrast. And this high contrast will create resonant poles to the corresponding linearized Hamiltonian. And these resonant poles, of course, calls for enhancing generated waves. And this enhancement can be turned into quantitative estimates for inverse problems. So this is, if you want, the story that part of the story that I will tell you today. Good. So what do we mean by this contrast? So I formalize it this way. Let this triplet D is the shape of the bubble. Let's say shape of the bubble. Rho and K. Rho is the mass density, and K is the bulk modulus. Let me tell you here we are using really the linearized acoustic model of the famous Kaflish and all bubbles model. Okay, so make it very clear from the beginning. And then with these triplets, then how we model it? We model it to be a gas bubble or bubble in short, if the mass density is very small and also the bulk moderate or very small. In this case, we take it also very small. This makes sense for gas, of course, because the mass density is very small. And then we design the size of the bubble so that we have this scale. And this scale, as you will see later, will appear naturally in our estimate. Okay. The other family, we call them liquid droplets. They are bubbles, but filled in with the liquids. In this case, the liquid and the bulk is very small. Again, same story here. It's very small, and you design the bubble so that you have this scaling. But the mass density is moderate. Okay? So one picture, you should remember that for gas bubble, we have both of the coefficients appearing in the acoustic model are very small, while in the liquid, it's the lower order coefficient that is small. Actually, that is large if you see it, because it appears as 1/k. Okay. Good. So, what do we mean? What do we mean by resonances in this case? Now, here is the PDE model corresponding to the linearized acoustic model I consider. So it's of this form, divergence form with this wave. And we define this domain. I think you all have seen such kind of models. And what is the particularity here is that this, according to the modeling of these bubbles, the gas bubbles, then the mass density is very small inside of the bubble and moderate outside. In this, for this part, I take it constant, and here also the same for the bulk. Okay. This Hamiltonian. With this domain is well defined in this pivot wave space. In addition to that, for each A fix, coefficient A fix, then we can talk about this resolvent from this space to this space. These two spaces are just local realizations of those spaces. Okay? And the resolvent of this operator, so this resolvent, is well defined, a meromorphic operator from this space to this space. So I give you here a reference where you can get this for those who are not used. In addition, due to the reality of the coefficient and the eventual poles of this Hamiltonian are located in our complex plane. Then mathematically, we say that zeta is a resonance for this Hamiltonian if it is a pole of this meromorphic operator. Good. Then if we restrict ourselves to forms of this way, so my bubble is written by as a center Y, let's call it a certain center Y, and it has a size A, and this is like any ball, for example, center 0 on radius 1. In this case, by scaling, we can compare the eventual resonances of this operator where D is B here. I changed the here, this D by B, and the resonance of the Hamilton of the original. So this is the original. So to study resonances for this operator, it's enough to study resonances for the scaled operator, and then do this scaling from zeta to zeta over A. Okay. Then let me now discuss this operator. What we could find recently is the following. For this operator, if you go to the real line, here, and you take these blue points are nothing but the Neumann eigenvalues for the Laplacian on B. So you take the Neumann eigenvalues for Laplacian on B. For instance, you take the trivial one, which is 0, and the other ones. They are here symmetric because we take the square. No? The only thing is we take the square. So if you take these eigenvalues, then each eigenvalue will be shifted down to create a resonance for our operator. Okay? So this is the message from this theorem. What we could prove is that we have a family of resonances near the real line, which are shifts of the Neumann eigenvalues for the domain B. And the length of this strip can be estimated around A, which is the radius of my bubble. Okay, so we have existence, and in addition, as soon as you fix an interval here, fix a finite interval, then these resonances are unique in such kind of strip. So we have existence, and we have local existence and uniqueness of these resonances, and we know where they come from. They come from the Neumann eigenvalues. But more than that, we have the asymptotic expansion of those resonances in terms of the size of the bubble. For example, for the trivial one creates two resonances with the signs, and then we can identify this coefficient. We can calculate it explicitly, and also the imaginary part we can calculate. Dominating imaginary part and dominating real part can be calculated explicitly in terms of our properties. Similarly, for the next ones, if you take the trivial eigenvalues, then they shift and give you this expansion. So this is exactly that Neumann eigenvalue. And this one also is explicit in some sense that these are explicit constants of our media. And these are eigenvalues of the following matrix, which is related to the Dirichlet-Neumann map. Okay? And we prove that the eigenvalues of this matrix has negative imaginary part, which means indeed confirm that the resonances are in our complex plane. So we have existence, we have uniqueness, local uniqueness, and we have asymptotic expansions. Now remember that these are the resonances for the scaled operator, and remember that we have said that we have this correspondence. As soon as we characterize a family of resonances for this operator, then we can say similar things for the original bubble type Hamilton. Okay? Therefore, if I use these asymptotics and I just divide by A, then I get the ones of my original Hamilton, which is here. For example, for the trivial one, as we divide for trivial one, this resonance is equal to this constant minus this term, where this omega m is sometimes called in the literature called the Minnaert resonance frequencies, and all this resonance is called the Minnaert resonance. And for the other one, for the other family, we have this scale. As you see here, please pay attention to this part. The next part stays small, but this part is large. So I wrote it here in blue. Or before that, the trivial or the Minnaert frequency, Minnaert resonance converges to the Minnaert frequency, which is given here by omega n, which is here. However, the other resonances, they become very large. And probably this explains why in the engineering literature, the Minnaert frequency, Minnaert resonance is the most useful, and most used, most announced. I never seen even really works discussing the other resonances, and probably because as the bubble is small, those resonances are very large, so they are not captured or something. Okay. And so this is the first resonance we retrieve the classical known Minnaert resonance, and then we added this sequence of resonance that we call Fabry-Perot resonances. Why? Why? Because due to their this eigenvalue having eigenspaces, and the eigenfunctions are changing sign, so we have interferences of the eigenfunctions. So they play a similar role as the well-known Fabry-Perot resonances. This is the reason why we call them Fabry-Perot resonance. And this appellation was suggested to us by Habib Amari when we sent him this corresponding work. So morality for a single bubble, we have a sequence of resonances, one which is subwavelength, okay? So it's this one which is subwavelength, and the other one which is wavelength. So if you see this, then if you go back here, then it's sheet clear. This one is subwavelength, but this is wavelength. Okay. So a few references about this. The original subwavelength resonance, Minnaert resonance, was observed and characterized several years ago by Habib Amar and his group. And they have done through it rounded wonderful results in imaging or material science. And the way how they characterize this Minnaert resonance is characterize a frequency for which the corresponding integral equation degenerate. This is enough to say as the integral equation degenerates, and the field generated is amplified, and this is enough for applications. So the way how they characterize it is related to degeneracy of integral equation. So for me personally, I had the curiosity to see whether this Minnaert frequency or Minnaert resonance is a true mathematical resonance, whether really you can see it as a pole of a certain related operator. The first tentative that we have done with Andrea Mantil and Andrea Posilicano is to relate this acoustic operator to a frequency-dependent Schrödinger operator. We want to really relate it to the Schrödinger operators. We could retrieve the Minnaert resonance, but we were not fully satisfied. And then instead of making this link from the acoustic operator to a Schrödinger operator, we stayed in the original acoustic Hamiltonian, as I showed before, and then we end up to see that this Minnaert resonance really is a true mathematical resonance for this Hamiltonian. So it's a true pole of the resultant of this acoustic Hamiltonian. And later on, we have seen that actually not only this low frequency resonance exists, but we have a family of those resonances, and the picture becomes clear that it's the Neumann eigenvalues that are shifted to generate resonances. So this is, in short, the story of those resonances that I described. Now let's move to the most important thing in this talk is how to use these resonances to do quantitative estimate inverse problems. So I divide the next part of my talk into three parts. In part one, I use the subwavelength resonance, or the Minnaert one, and I show you how we can tune it to give a local reconstruction of both the mass density and the bulk. Okay, so, and this we use them in isolation, as I said in the beginning, so we put them in isolation. In the second part, when we send them as a cluster, so we put many resonant bubbles. In that case, we propose an effective linearization of the scattering map of the Dirichlet-Tuman. So we get rid of the nonlinearity of the Dirichlet-Tuman. And the third one, which is more exciting to me, is that if we move from the subwavelength to wavelength, then things become even more interesting. And I will give you one application where this could be helpful. Okay, let us then start by the part one. So subwavelength resonances for local reconstructions. Okay, a schematic design of the experiments is as follows. So if you remember the pictures before, the left-hand side here is the experiment before injecting the bubble. And here, second one is the experiment after injecting the bubble. So we would like to give information about the background. We send wave and we collect the wave in a certain receiver and then try to do inversion. So what we do here, we measure before and after, and then we contrast the two images or the two fields. So the measurements are a differential field U minus V. U is the one after, V is the one before. So if we allow this, Then we can apply this idea for the time domain imaging and the time harmonic imaging. And this is the speed, and the unknowns are K naught and Rho naught, so the bulk and the mass density of the background. Okay, so we apply it for time domain and for time harmonic. Let me start with okay. Let me here recall you the scales. According to these scales, you know that we can wait for having subwavelength resonance, which is the Minnaert resonance. Okay? And if we do the calculations of this resonance inside a background medium, then the observation we made is that the dominating part of this Minnaert resonance has an explicit signature of the mass density of the medium where we put it. Okay, so imagine you are in medium omega, you have rho naught there is variable, and you put a bubble inside, then the resonance generated by this bubble is created by the mass density on the point where the bubble is located. Okay, so the Minnaert resonance inherits the value of rho naught in the point Z. Therefore, it's natural to ask the question: is there any way to do an experiment where this Minnaert resonance can be recovered as a resonance? And then, if it is recovered as a resonance, then we can have access to the medium on the point where on the location of this bubble. Okay, so this is the idea. So we turn the problem into recovering or detecting resonances. This is what we propose here. So sorry for those who are not used with this terminology. Here we use it in time harmonic. V infinity. This is nothing but the far field. The field that we collect far away from the background when we excite the background by plane waves. Okay, this is before injecting the bubble, and the first one here after injecting the bubble, and we do the same experiment. So you send the plane wave and you collect the far field data far away. Then you see that the difference is dictated by this element, where here you have a resolvent denominator. Of course, we are talking about resonances, and we have a rank 1 residue here due to the fact that this first subwavelength resonance is simple. Okay, so in terms of our inverse problem, so we have this resonance which depends on mass density, and we have also this field V, which is nothing but the field before injecting the particle, the bubble. Okay. So based on this asymptotic expansion, then we build an imaging functional. Imaging function is given here in blue, and this I choose here as a direction. The direction here I choose the backscattering direction. So it's exactly the direction where I send the wave. I collect the wave coming back from that direction. Okay? So if I use the backscattering direction this way, then the expansion before tell me that this indicator function or imaging function is given by this quantity. Okay, so then what we say, then we repeat this experiment in a band of frequencies that large enough to contain this interval with these values, which means here we need to have a priori information about the mass density as the minimum and the maximum, or just take the band large enough. So if you redo the experiment, you bombard it by incident wave, you measure in one direction, and you repeat it in frequency. Okay, so you have only one direction of measurement, and repeat the experiment in terms of frequency. And what you do then, look at the behavior of this function in terms of the frequency. Then you get such kind of form, and this form obviously gives you that the peak here is reached near this Minnaert frequency, and also the residue can be estimated. Okay, so just look at the behavior of your measured field in terms of the frequency used. You can have access to this information. Then, if you have access to this information, then you go back to the definition of characterization of this resonance. Gives you the explicit value of the mass density on the. Okay. So then if you repeat the experiment, as I say, you put them one by one, you put the experiment inside, then you can have an idea of an estimation of the mass density inside omega. Okay. In addition, I said that we can get the field before injecting the bubble on the point on the center of the bubble. So if you do also this scanning, then you have access to this field. But this field solves this equation. Okay, so at the price of numerical differentiation, you can calculate this K0 by dividing by V, which means that you can reconstruct the bulk wherever your total field is not very small or is not little. So as a message, based on this resonant effect, it's enough to look at the behavior of the measurements in terms of the incident frequency to reconstruct the mass density and the bulk. Okay, good. Now let me move to the time domain. The time domain. I start by this time domain. We are using here integral equation, so we use the green function for the background. Then you see here the green function has this behavior. It has a singular part and this regular part, and these coefficients can be calculated. So I ask you to accept this kind of singular decomposition of the green function, because this is the key in doing the inverse problem. And these coefficients are fully, here zeta is the travel time function. This is zeta travel time function. And all these coefficients are given here, they are characterized by our coefficient K0, the speed, and travel time. Okay? So we have this singularity, this travel time, and we have this coefficient. Good. Then what we do similarly as in the time harmonic regime. So we get the data before injecting the bubble, the data after injecting the bubble, and then you contrast the two data. If you contrast them, then you can have the dominating term here. Sorry, I should talk about this. The dominating term here satisfies such a Volterra form, Volterra integral equation, where this kernel obviously is related to this singularities here. It has, so there is a geometrical singularity and there is an inherited oscillatory kernel. By using this representation, then we prove this property that this measured wave field in time is zero or small. Here, zero for the dominating part is zero if t is smaller than this travel time. This travel time is the time needed for a wave to go from the point of where we send the source to Z, which is the center where we put the bubble. Okay, then this field is zero before that time, and this field is not zero after that time. Okay, so this discrepancy allow us to localize this the value of this travel time at the point Z. Therefore, if we repeat, we add other bubbles inside, then we can have access to this function in terms of Z. Okay, so we have access to the internal values of the travel time, and then embedding it in this Acoustic equation, we can reach the values of the speed of propagation. Okay. So if you compare this to the time harmonic regime, time harmonic, we said look at the data in terms of frequency, you solve the problem. Here we look at the data in terms of time, we can recover the speed of propagation. We can also recover the speed of propagation, because speed of propagation is given in terms of K0 and ρ0. We can separate them by, in addition to looking at the zeros of this measurement, look also at the slope. If you look at the slope, starting where it starts, then we can calculate the coefficient that I showed you before. And this coefficient is naturally related to the bulk as soon as you know travel time and the speed, and travel time, which means that we know the speed. And this coefficient is related to travel time. So all this coefficient is computable as soon as we know the travel time. And from this formula, from the slope, we can get this coefficient. Therefore, from this coefficient, we can have access to K. So the morality here is the following. For each location of we put bubbles one by one, and we measure the differential data. Differential data, and then look at the behavior of that curve in time. This behavior gives you the birth. I call it the birth time, and this birth time is the travel time on that point. If you put more bubbles, then you can have access to this function and use the Acoustic equation to solve for C0. Then go back to that function, look at the slope, and from that slope you can get the mass density and the K. This is the way how we can separate between the mass density and the bulk. So the message here is then, again, look at this measurement in terms of time can solve the problem. Okay. So this is our understanding how to use the resonant effect to have local reconstruction by putting the contrast agents one by one. Now I give you a situation where you put this contrast agent as a cluster, and in this case I use droplets instead of bubbles, simply because we wanted to test this idea on a very popular problem, which is the Calderon problem. So I state here the Calderon problem. So P is the pressure, solve this equation where M is the index of refraction. And we have this Neumann-to-Dirichlet map, and the classical problem is to use this Dirichlet-Neumann map to get the index of refraction. And this problem is nowadays classical, very much studied, and we know that there are two classical difficulties in this. First one is this is highly nonlinear, and second one, it is very smoothing, which means the inversion is unstable. What is interesting to me here is to tell you that this nonlinearity, we can do something if, in addition to this measurement, we can perturb it. If we can use perturbation, a contrast agent as using droplets, then we can linearize. This is what I will show you next. So here we take the cluster of our droplets this way. Now they are droplets, so we have contrast. Let me remind you the contrast in this case. This is a liquid, so the mass density is moderate, but the bulk is small. And in this case, we have droplet resonances. I call them droplet resonances, which means that our system creates resonances parallel as those I said before. But here, these resonances, they come from the Newtonian operator, not from the Neumann operator. That's the difference. So for bubbles, for gas bubbles, we have the Neumann eigenvalues, and for droplets, we have the Newtonian eigenvalues. Okay. So I take the Newtonian operator on the scaled droplet. I compute these eigenvalues. I choose one, and then I choose frequencies close to this chosen eigenvalue in this sense. Okay? So here A is the diameter or is the radius of my droplet. Okay, and this coefficient Cm is taken here negative. I put here this in red. We need to take it negative. You will see later because whenever we put this, we inject this cluster of droplets, then we can hope to get effective media, which is negative, and this is the key. Okay? So the sign matters in this case. Good, then we distribute these droplets in a periodic way, estimation this way if you are interested. Then if you inject them there, then the modeling after injection is given by this model. So this is the previous one, and this encodes the local inhomogeneities. And then to this problem where we have periodic perturbations, we can think about the homogenized model, and the homogenized model is characterized. It's here, so it's a shift. And you see here the sign is important to me, as I showed before. And this P now, which is a constant, can be calculated, can be estimated in terms of the eigenvalues and the eigenfunctions of the Neumann, the Newtonian operator of the droplet. Okay? And they call lambda P now the Neumann-to-Dirichlet map of this effective medium. Okay? So we start from the Neumann-to-Dirichlet map for the perturbed one, and we end up with the Dirichlet-Neumann map with the effective medium. Indeed, this can be estimated, and there's some smoothness. Then we can show that the Dirichlet-Neumann map of the perturbed medium converges to Dirichlet-Neumann map of the effective medium with these estimates. So in principle, if you measure after putting the droplets, then you can have access to the measurements of related to the effective map. Okay. Good. Now, then, if we have access to the effective map, then actually we can linearize the corresponding Neumann-to-Dirichlet map in that case. Now we linearize it around the absorbing model, which is here. So I take this model and I can linearize the Dirichlet-Neumann map around this, and this is given by this theorem. So the Neumann-to-Dirichlet map for the effective medium minus the value, this value, which is solution of this problem, is given by this blue part plus something which is small, and this blue part is nothing but the source where the index appears as source for this problem, which is the linearized part. Okay, so if I have access to this I can generate it. Therefore, I can have access to the values of this. Gamma here is the trace, is the Dirichlet trace. Okay, then now we are in the linearized problem. We can go to the classical ideas to solve the problem. One of them is to use the Calderon idea using CGU solutions. So we can, from this measurement, we can have this product where V and QF are solutions of this effective equation, which can be generated. Then if we use proper CGU solutions, then we can have access, as you all know, I guess, to the Fourier transform of the index of the fraction. Okay, so the morality, if we have access to the Neumann to Dirichlet map for the perturbed medium with the droplets, then we can linearize the Neumann to Dirichlet map. This is the message. And then while linearizing, then we can do explicit reconstruction by CGU, for example, or any other method. Okay, so this is the message. And the tuning the resonance is very important. So this sign is very important. If it is a plus, then this linearization is not possible. It's very important. Let me go to the last part 3. Now we move from subwavelength resonators to wavelength resonators. In this case, the Fabry-Perot resonances. How can we use them for the inverse form? What do we learn? So here I put my interest a bit down. Because we are just starting investigating imaging or wave propagation at such kind of wavelength regimes. So I put myself in a simpler goal. The simpler goal is to say that you injected such kind of bubbles. I would like, and you want to localize them or reconstruct them by using their generated scattered or far field. Okay? So this is a typical inverse scattering problem of localizing and reconstructing, localizing and reconstructing shapes. And as this is small, then of course one could think of several sampling methods like music. And then let me recall you, for those who know, or for those who do not know, that at fixed frequency, at subwavelength regime, the only thing we can expect here is to see a contribution given by point-like scattering. So we see this bubble as a point-like. So we can only localize its center, and give an estimation of the scattering strength, which is here the capacitance in this case. So we can localize the bubble and estimate its size. Let's say to draw an equivalent sphere. This is what we can do. We cannot do more than that. But if you go to the wavelength regime, then you can have access to more data about your shape. Namely, I'm interested in sharing with you this. We'll get access not to this capacitance type estimate, but to the far field data of B. So remember that D is the scaled of B. Then if you measure the scattered field generated by this one, then you can get access to the far field generated by B. This is the message I want to give you if you do excitations at the wavelength regime. To do this, let me tell you how we do. So you start by Z0 is a Neumann eigenvalue, a non-zero Neumann eigenvalue of the Newtonian, and then you excite it with you take incident frequencies close to this Z0 in this regime. Okay, in this regime. So with this, so you see that the frequency is very large because it's multiplied by A, which is small. So in this regime, we do the images. So we have this expansion. Sorry for this unfriendly formula. So what I just want to tell you that the scattered field measured at some point x have a direct link to this element, and this element I write it here is nothing but the far field for this problem. So the exterior Dirichlet problem. So you have this Dirichlet exterior problem, and you generate from this source, you generate the far field, and this far field appears in here. You don't need to see the details, the calculations here. You see that there are appearance of the eigenfunctions of the resonances or the eigenvalues of the Newman eigenvalue, of course. But the most important observation is to link the scattered for D to the far field for B. That's the most important observation. And then with this information at hand, then you say that if I measure the scattered field for a small bubble at certain point x, but I do it in a large band of frequencies, then it makes sense, it is reasonable to have access to the Neumann eigenvalues of B, or more than that, you can have also access to the far field generated by B in this direction. So you fix direction x, you get the far field in this direction, where Z is the center of the bubble here. Okay. So if we excite at wavelength resonances, then the small bubble is seen as an extended one. This is the idea. And then, according to these two data, we can state the problem as either as a CAC, very classical CAC type question to recover information of B from its Neumann eigenvalues, or typically from Schiffer's scattering inverse problems, where if we have access to this scattered field in different points x on a certain surface, and then which means that you can have access to more incident or observation directions for this far field, and you can reduce the problem to the classical inverse problem. So morality, Fabry-Perot regime provides scattering data tied at the Neumann spectral geometry. So we go from this regime, we go from information of the small scatter and look at it as a large scatter with that kind of spectral information. Okay, good. So let me summarize this last part. What I wanted, the message is that if we do imaging at Minnaert at subwavelength regime, that what we can get are location and size estimates. But if we do it at Fabry-Perot regime, then we can expect more than that. We can have far field pattern for an extended one, and therefore we can expect shape features. There is also anisotropy that we did not talk, and this is very interesting. This kind of appearance of the anisotropy, because we observe that if you have multiple of such, then if you want to think about effective media, then the picture changes. So the picture is different from subwavelength homogenization and wavelength homogenization. Namely, in this case, in the wavelength homogenization, we have natural anisotropy that appears, while in subwavelength regime, everything is isotropic. Okay, so summary of this part 3, at the Minnaert resonance, the small object is mainly a point scatter, while at this wavelength resonances, we have shape-sensitive resonate. Okay, now we have 2 minutes or 3 minutes, yes. Here I give you this last slide is about big unified picture of what I said. So I started by telling you how we can characterize resonance generated by high contrasting media, in our case bubbles, and then we said that if we inject the bubbles as application for the inverse problem, if we inject the bubbles in isolation, then using the Minnaert pole we can recover local information about background. If we use clusters, then in that case we can have access to the effective negative potential. So we can have a negative shift of the model, and this negative shift allows us to linearize the boundary map, so that you can get, in principle, an explicit solution at the end using, for example, CGO solutions. And if we move from the subwavelength to the wavelength, then the picture becomes even more interesting. I gave you an example where a small scatter becomes a large scatter at that large frequency. So we can expect not only localization, but also shape sensitive signatures. And they give an example of those either using CAC or Schiffer inverse problem, but of course you can use other tools as well. So I hope I was not too quick, yes, so this is really the message I wanted to share with you, and I thank you very much. I finish my talk by stating here the main references I used to build up this talk. The first part is concerns the time harmonic regime I discussed before, how we use the data in the band of frequencies and do reconstruction because of the resonant effect. In the second part, we do it in the time, so it's this problem mainly. It's this problem, but we do it in time domain where the analysis is more involved. So we could show all those estimates, expansions that I used here quickly, but their analysis, of course, needs some work. For the linearization, when we use the droplets, this comes from this work. We apply it for the Calderon, and for the resonances, the study of the resonances, and this going from point-like to shape-sensitive resonances can be the analysis can be found in this last paper. And I thank you very much for your attention.
Great. Thank you so much for a very nice talk, Mourad. So if anyone has questions, please free unmute yourself and ask questions. So I was wondering a little bit, Mourad, so you mentioned up front that one next interesting chapter perhaps to look at is where you have random locations. Do you think what would be the interesting challenges or also applications for such a center?
There are many challenges. There are many challenges. For example, I gave you the analysis at subwavelength regime. I gave the analysis in two extreme regimes. One, we put them one by one. In the other one, we put them all at once and with some structure. We need a structure. Can we do in the intermediate? What can we do in that? What does it mean? What are the regimes in between? Because I think the reality is more in the in between than in the two borders. So I put myself in situations where I can do analysis, but the natural thing is to see what happens in between. And also when we have randomness. So can we transport this to randomness? For example, this effective idea, I guess this can go. I guess this can go. But more, and then another big project is to go to go from subwavelength to wavelength. Can we do imaging at the wavelength regime? So I don't know if there are. I looked around in the literature, mathematical speaking, I didn't find that many results at those wave scale results. I think there we can find many interesting results, I guess. But the challenge is, of course, is higher. What else? And then the other models here I discussed ultrasound, but you know, like me or more than me, that there are many other imaging modalities that can be tackled with same ideas. I can think of optics, we can think photoacoustics, they're all the same thing, and many others. The principle is, as I showed it in the picture, I showed you three. There is MRI, there is photoacoustic, and there is another one, I forgot, Raman scattering. Imaging using Raman. All this, they use the same thing. So can we quantify such kind of ideas through the resonant behavior as I described it? So there are many things to do.
Yeah, thanks. Yeah. Any other question for Mourad?
I just wanted to ask a quick question about so I guess these higher modes, you know, your FP resonances, is this like kind of like does this usually occur in like some lossy acoustic cavity, or can it be viewed as like cavity like resonances, or is there any more intuition?
I deeply agree with you. So here I put myself in the linearized model. This is not a challenge to continue with the question of fluid. We use really the linearized model where we can do things. But I agree with you. If you go back to the two bubble model, then here we miss, for example, surface tensions, and in that case you have cavities. Yeah, actually the situation is much richer in that case, but it's more difficult. For example, Here I'm telling you that the resonances are coming from contrast of the coefficients of the media. But if you add surface tension, then you can have the surface move, the surface vibrates too. And we have lump resonances, another family of resonances. So all this, if you want to go into the closest model, then we can indeed talk about cavity.
Okay, thanks.
Yeah.
Great. Well, if there are no more questions, let's thank Mourad again for a very nice talk and interesting perspectives on bubbles.